Thanks everyone for joining. We're going to talk to you today about a project we've done for Pinellas County, Florida in the United States, a vulnerability assessment looking at sea level rise. And this is a coastal community, so a lot of concerns, of course, with sea level rise and climate change in this area. My name is Chris Dorney. I'm in the climate resilience and sustainability practice in the United States. I'm a director in that. I've been working on climate adaptation since approximately 2009, and lead a lot of our climate adaptation work here in the United States. I'm based in our Lancaster, Pennsylvania office in the United States. I'll turn it over to Justin now to give an introduction. He'll be co-presenting. And Justin?
Thanks, Chris. Hi, everyone. Thanks for joining in today. I'm Justin Lennon. I sit within WSP USA's Water National Business Line, where I'm a national practice lead for hydraulic structures and flood control, basically handling a lot of river engineering topics. My ties to climate resiliency and working with Chris and the CRS team goes back nearly a decade with the firm, and we've looked at a lot of interesting projects around the United States, working on how to incorporate climate resiliency and climate change into adaptation design. So we're excited to present this this particular project in Florida, and I'm going to turn things back over to Chris to start us off.
Okay, thank you, Justin. Talk through the agenda. First, we're going to give you a little background on the project, discuss its scope. The two main parts of the project we'll then talk through. I'll discuss the county-wide risk analysis, and then Justin will pick up and talk about some of the facility level adaptation assessments that we performed. And as mentioned before, we'll have a time for questions and hopefully some answers for you at the end. So what was the scope of the project? Again, two main parts, a county-wide risk analysis and then some facility level adaptation assessments. The county-wide risk analysis entailed looking at two types of hazards, tidal flooding and storm surge, and looking at them for today's conditions and also in the years 2040, 2070, and 2100 under three different sea level rise scenarios. And for those of you that are not familiar with Pinellas County, it's located in the state of Florida, which is in the southeast part of the United States, and it's on the western shore of Florida, which is itself a big peninsula, on the Gulf of Mexico side. This is the Gulf of Mexico. And Pinellas County is itself a peninsula, so a peninsula on a peninsula. This is the county outline here that you're seeing in red. So again, needless to say, a lot of concern there over sea level rise and storm surge. Certainly hurricanes are a threat in this area. So we wanted to be able to map those hazards both today and in the future with sea level rise. That was a key part of the scope. And from there, we wanted to be able to assess the exposure of public infrastructure, be they roads, buildings, what have you, and then quantify the risk of those assets to flooding from tidal flooding and storm surge. And we didn't do that for all the assets. We didn't have the resources to do so, but we did it for a subset of roads to pilot the approach. From there, we also did facility level adaptation assessments, and these are more site-specific assessments of what you could do to adapt that particular facility that was determined to be at risk. We did 5 of those, and again, Justin will talk about some of those, subset of those later on the call. This project does meet some of the UN Sustainable Development Goals that WSP is committed to furthering. The two that are most relevant that this project covered are Goal 11 on sustainable cities and communities and Goal 13 on climate action. All right, so as we focus on the county-wide risk analysis, the first task that was before us was to do that hazard mapping. you're seeing the outputs of that on the right here. These are an example of the tidal inundation flooding that we've mapped out, and this is some example of the storm surge mapping that we've done. So tidal flooding, we're essentially talking about here sunny day flooding absent a storm event, something that is already happening in parts of Florida, including in Pinellas County, and will continue to be more of an issue as sea levels rise. What we did for this assessment was something that goes beyond a lot of what others have done in the field. You'll often see mapping of mean high water and mean higher high water. Those are if you're in an area with too high tides, mean higher high water is the higher of the two high tides, how far that gets in, and mean high water is the average of the two high tides. So that's often the extent of the mapping that you'll see is what gets wet during the higher of the two high tides. But if you think about it, not all, that's an average, right, of tides. And certain days, the tides actually get higher than the average. And that happens frequently throughout the year. So if you really wanted to understand what gets wet, and some things, if they get wet just once a year, that's a big concern. You wouldn't want your house to get wet once a year. You wouldn't want electrical infrastructure to get wet once a year. You need a higher threshold of tides to be able to understand really what's exposed. So we did some mapping of the frequency of tidal flooding, which is, by the way, we need that also for supporting the risk analysis. We need frequency information. And we did it in terms of hours per year of inundation. So we looked at areas that get wet 250 hours per year, 50 hours per year, and just 1 hour per year, which is actually the highest flood inundation and the greatest extent of our tidal flood mapping. And that really allowed us to, and the client to understand better and be better prepared for the areas and assets that will get flooded. To do this, we leveraged astronomical tide predictions, which is available from our National Oceanic and Atmospheric Administration in the US, actually out through the end of the century, since we know how the planets will align and the moon will align. We are able to do that. I should say the sun and the moon are the main factors there, not the other planets. But those predictions are available out through the end of the century. We also developed a spreadsheet tool to support this, and it's capable not only of for a given elevation that you provide it, showing the hours of flooding per year at that elevation, but also the number of flood events per year, the average annual duration of flood events, and the maximum annual duration of flood events. So it's very useful and powerful information. And then from there, from that spreadsheet, we can then translate through another process those elevations and those hours of flooding per year into maps like you see here. For storm surge, we looked at several different return periods of storm surge inundation. The 25-year, the 50, the 100, 250, and 500-year inundation areas were all mapped. Again, that breakdown in frequencies is needed to support risk analyses, which we will do later in the project. This is an effort that we subbed out to the University of Florida, and they used their hydrodynamic model that they created to do that storm and wave modeling. Storm surge and wave modeling. One unique thing that we did on this project is consider not only sea level rise, but the climate change impacts on tropical cyclone climatology. So there's some research out there showing that in certain areas we might get perhaps more frequent storms, or maybe not as frequent but more intense storms. We looked into that in the area to see if that could inform our modeling. In this particular part of Florida, we found that there were no notable effects on the climatology of storms, at least according to the current science. I know that differs in other parts of Florida and certainly other parts of the world, but it is something that should be looked into, and we can help you do so if you have any questions about that. All right, so what this mapping did is, like I said, to support the risk analysis, give us a real good frequency distribution of flooding for any given asset, any given area. And you're seeing here that combination of tidal flooding and storm surge by frequency across the landscape. It's very high resolution data based on LiDAR elevation data. So we're getting to about a 1 meter accuracy, and so it's pretty useful and neat to look at as well. And then we can of course see how areas of flooding will expand into the future and how the frequencies will go up. Okay, once we had created the hazard data, we needed to do the exposure assessment. And for that, we developed several GIS models to do the overlays of the hazard mapping for all those different time periods and sea level rise scenarios and return periods onto an asset database that we worked with the county to put together. The assets that we looked at and for which this GIS model does exposure assessment includes transportation assets like roads, railroads, and airports, but also other utility infrastructure like electrical infrastructure, potable water infrastructure, wastewater, and natural gas infrastructure. We also looked at stormwater outfalls and the percentage of those outfalls, the percentage inundation of those outfalls. We didn't do full-scale stormwater modeling. That wasn't part of the scope here, but we did sort of the first pass at looking at where those outfalls might be blocked due to storm surge or tidal flooding as sea levels rise. Needless to say, we found, unfortunately, widespread exposure throughout the county to several of the different asset types. The final stage in this county level, community level, or systems level assessment was quantifying the risk. And when we quantify risk, what we're trying to do is baseline the cost of an action with an estimate of do-nothing costs for each asset that would be, incurred if you didn't do any adaptation. These are the costs, that would be incurred through the end of the century. Those costs, these do-nothing costs, consider both physical damage costs and user costs as well. And then those costs can actually be used to prioritize facility level adaptation assessments and where you take action. Those assets that have the highest cost, the highest risk, are the places that you probably want to focus first for more detailed study and eventual adaptation action. Like I said, we didn't have the resources on this project to build out the risk model for all the asset types, but we did do it for a subset of roads. We did a test demonstration on 36 roads. So we built a roadway risk model. This considered, from a damage perspective, pavement delamination potential due to storm surge, also pavement damage just due to regular tidal flooding inundation. We also considered embankment erosion. If a roadway's on an embankment and you have surge going over that, or even a high tide event, that can erode the embankment. We considered that and tallied those costs. For user costs, we have developed a GIS-based automated detour routing algorithm. So if a roadway were shut down, say this green road here, this GIS-based tool will look at the shortest path detour route around that particular area of impact, and we can use that in combination with assumptions about the time value of travelers and also fuel costs and wear and tear and that sort of thing to estimate what a detour would cost. And essentially then we put these damage costs and the user costs together in a risk quantification model that we've developed, and this one is Monte Carlo based, and that gets us through some math to those do-nothing costs over the life cycle of the assets through the end of the century. And with that, I'll turn it over to Justin to talk through the facility level adaptation assessments that we performed.
Thanks, Chris. So after the team has gone through and done the risk assessment for the entire county, we identified a number of assets that were at risk, and we took those into a more detailed pilot level study to take a look and say, okay, what do the risks look like at these facilities? what are the chances that we're going to lose critical infrastructure and what can be done about it. Under the Pinellas study, we looked at 5 different pilot studies. One was on, or 2 of them were on roadways, one at a stormwater outfall, one at a wastewater lift station, and one at a water reclamation plant. So I'm going to walk through the wastewater lift station and the water reclamation plant examples. Both of these examples, as well as our other ones, utilize the ADAP, the Adaptation Decision-Making Assessment process, to walk through the study and the incorporation of climate change into the analysis and design and adaptation design of these facilities. This is a process that WSP has developed, working with US DOT to help guide engineers as they're making decisions on how to incorporate future climate data into engineering design. We built this process to avoid any type of instant reaction where you would want to just look at the highest climate data, but rather consider the full uncertainty, the full spectrum of what the future climate models are telling us, and make best value decisions for infrastructure. Next slide, please, Chris. Next slide. Okay, so our first study is going to be on wastewater lift station 163. Next slide. So this is located on the Barrier Island, just off of Pinellas County. So the Madera Beach, Reddington Beach area. This is on Sand Key. Currently, this particular wastewater lift station collects discharge from 2 square miles of basin area that includes almost 4,500 households serving this area. It operates as part of a chain of lift stations that convey the wastewater off of the barrier island and onto the main island for treatment. Next slide, please. So the site itself, the lift station, all the electrical equipment is housed inside the building in this photo here. You can see the vent stack off to the right of the photo that feeds the wet wells. So the wastewater comes into the wet wells for pumping into the building. It gets pumped, the major pump and generators located in the building, pumped into the pressure flow wastewater lines and conveyed off the island. Also of note, outside of this panel is an electrical, or outside of the building is an electrical distribution panel that provides the daily electricity to run this wastewater lift station. It's one of our focuses in the study. Next slide, please. So this schematic basically lays out how we looked at the pump station building itself versus future climate. We're showing our different levels of current and future storm surge at this structure. Given that we are very coastal here out on the barrier island, our primary flooding threat is hurricane storm surge to flood this island. So we looked at our different return periods and how they changed into the future and looked at how that threatened this particular building. So our lowest elevation threat that we took a look at were the wet well access hatches. So basically, these doors are not particularly watertight. Surge does have the ability to flow into there. However, the wet well itself is just where the wastewater collects. The intrusion of water into there is not particularly a fatal flaw with the system. We expect that there are a lot of points in the wastewater system throughout the barrier island where storm surge is going to be able to enter that system. It's not going to damage any of the equipment. It's just additional water that would need to be treated. Next up, we have the vent stack, basically the same situation. It's a pathway for water into the wet well, but into the wet well does not mean it's going to get into the facility. The electrical distribution panel, we have the bottom of that sitting at elevation 8.3 in feet. So, what is that, about 2.5 meters above sea level. At that point, we can start to short out the electricity to the facility, so the pumps themselves would shut down once that goes out, but we do have a backup generator inside the facility, so we would be able to maintain operations. And then you have to go all the way up to the top of the building. The building itself is dry waterproof. The front door is basically like a submarine hatch. It's fully waterproofed, and it's got the dog latches to hold it shut. Up at the roof line itself, however, we now have the exhaust vent for the generator. So at this point, water would be able to get into the building, short out the electrical equipment, and we would have a real mess on our hands trying to get this facility running again. Next slide, please, Chris. So as we start to take a look at adaptation options and run things through the ADAP process, we looked at two different options. The first was to raise that electrical panel. So if we can bring this up and maintain normal operations as long as possible, what would that cost and what are the benefits? And then the second option is, okay, what if we like fully waterproof this structure, raise those roof vents so that we don't lose the function of the generator? What does that mean for us at this site? And one thing to point out, when we look at the facility itself, damage to the generators, damage to the electrical panels, there's a value to that, but it's not particularly high. We're not talking about a very expensive piece of infrastructure. However, we are talking about a pretty critical piece of infrastructure for the recovery of the community. At the point in which this pump station is flooded, there's going to be a lot of damage to the community at large. And being able to restore service to the area is going to be pretty important to the recovery of the community. So we really kind of valued that. And when we look at the ADAP process down here, we have step 9, evaluate additional considerations. And that really kind of became a critical point in this study, is evaluating the overall value of restoration of service to this community and allowing recovery to occur. Next slide, please. So ultimately, for this site, when we looked at it, we recommended or recognized that it is already fairly resilient, given that the building's waterproof and our low-lying failure points are really not particularly critical. And we recommended just the first option of raising the electrical panel. It's fairly inexpensive at 10,000 USD to take that step and basically allow for a quicker resumption of normal operations to the community. Next slide. Next slide, please. Okay, so then our last example that I'm just going to hit really quickly here is the water reclamation plant. We evaluated this plant also for vulnerability to sea level rise and storm surge. The site did demonstrate some vulnerabilities under its existing condition. However, those vulnerabilities were to low-lying electrical equipment. The main tanks that were storing water, drinking water and wastewater, sit high enough that they are not particularly vulnerable, and they're fairly well sited as they currently sit. Next slide, please. We took a look at two different adaptation options on this one. The first was dry flood proofing of the control buildings, basically adding waterproof hatches and doors and movable barriers to prevent flooding from coming into the buildings that are housing that electrical equipment. A fairly cost-effective option at $400,000 USD to protect this particular facility. And then the more Cadillac option would be to put a flood wall around the entire site, which we valued that option at about 25 million USD. Next slide, please, Chris. And the recommendations that we reached for this site, once we considered the totality and the how critical this piece of infrastructure was for the larger community, was to do a tiered approach, where under present day, we do some of the more inexpensive flood proofing options, and then long term, as future climate is getting worse, we look at the more expensive options and putting the flood wall protection around it. As we went through the ADAP process for this site, it recognized that the trends as they increase into the future do necessitate greater protection for this facility. However, the trends as things currently sit are not too critical. So we could go with more half measures at the moment and then adapt and include the more expensive ones into the future. Next slide, please. So that is the conclusion of our presentation. Overall, what we've presented here shows an application on how we could include climate resiliency into the overall planning for the community, as well as our two examples on how climate resiliency informed future design options for two critical pieces of water infrastructure. Now I'd like to open things up.
Thank you, Chris and Justin, for your presentation. It will be good if you can open your webcam. It will be great to see you. So before moving into the short Q&A period, I would like to remind attendees to enter your questions in the question box on the GoToWebinar platform. And also you can download the PDF version of this presentation from the handout box on the dashboard. I will start with the first question that we received. How was uncertainty in future sea level rise quantified in the analysis and then communicated to the client?
Yeah, I can take a shot at that. So as I mentioned, we considered 3 sea level rise scenarios. These were based on, at the time, the latest sea level rise projections available in the United States. That was a study done by the National Oceanic and Atmospheric Administration in 2017. Now, they've actually subsequently done another study just released this year, which updates those. So we'd want to update the assessment then, but obviously we don't have a contract to do that yet. But yeah, those sea level rise scenarios were selected to give us a range of what the future might hold. There was quite a bit of range. We looked at, I think, something like, the lower end was around 2 feet or so by 2100. And the higher end was perhaps as high as 8 feet or so. And sorry, I'm speaking in English units as opposed to metric. Hopefully you can Google that and translate if you're more familiar with the metric system. But quite a wide range in the projections were considered to try to sort of bound out the assessments. And that's a practice that we do for all of our assessments, is look at that full range. And we look at that full range both for the community-wide or systems level assessment, risk analysis, and then also when we look to the design options for any given location. That's what the ADAP process that Justin presented is all about, is as he mentioned, making sure we're considering the range of potential future scenarios and looking for the option, the design option that is really the most robust and best performing option across the range of uncertainty. I know there's a lot of practice out there that's emerging where, it's just, pick a scenario, pick a climate scenario, pick a sea level rise scenario. And we found from all the work that we've done that that's just, unilaterally or arbitrarily pick a single scenario. You could be making some very poor decisions based on that. And so I'm glad this question was asked because it is always very important to look at the range of uncertainty in climate projections, which can often be pretty substantial and have very different implications for design. So I don't know if you have anything to add to that, Justin.
No, I think that was a sufficient answer.
Thank you. We have a few more questions here coming. Does your inundation mapping take account of hydraulic connectivity to the sea, or is it purely a LiDAR level-based approach?
It's a good question. It is a purely elevation-based approach for tidal flooding. The storm surge mapping through the storm surge model would have considered the hydraulics. So tidal flooding, not so much on the hydraulics, it's more an elevation or quote unquote bathtub approach, whereas the storm surge mapping, because that was actually using a model, was considering hydraulics. Now, the question about connectivity, that part of it, so with both sets of mapping, storm surge and tidal flooding mapping, we did do a connectivity analysis to see if there was overland flow paths from any given area of inundation to the sea. And if there was, or if there wasn't, we coded those areas differently if there was not. So those areas that don't have an overland flow path to the sea, we call disconnected areas of flooding. And you have to take those with a bit more of a grain of salt. A lot of them actually are likely to be flooded during an event, but but some may not be. And so we do make that differentiation, and we make that in the reporting for all of the exposure. Why would you have disconnected areas? Well, if you have say a roadway embankment that's in between an area of water and some low areas on the other side of that, further inland, that can be sort of a barrier to flooding. But often there's a culvert, right, in those roadway embankments. Now, we weren't able to model the flow of water through that culvert, but the being able to show those disconnected areas of flooding on the more inland side of an embankment like that would serve as sort of a rough proxy for a planning level assessment like this to indicate areas of potential inundation. So
yeah, the thing I'd add to that is we do a lot of coastal modeling in the US, and we'll do full dynamic modeling of these surge conditions, but this was just a planning level study. So as a planning level study, it was appropriate to just do the elevation LiDAR based mapping on this particular case.
Thank you. Next question is, are tides alone really a problem? Does the surge analysis include all effects like tides, surge, and sea level rise?
I'll take a shot at that for the systems level assessment. The first question was, are tides alone a problem? Tidal flooding alone? And yes, it is, very much so. Especially the further south you go in Florida, it's even lower. So in Miami and Miami Beach, they regularly see inundation there at high tide during certain times of year where we get higher high tides than the average. And even there are parts of Pinellas County where that's already happening, some of the very lowest areas, probably, I don't know, a dozen or a couple dozen at this point. Going into the future, that's going to become, as I was saying, much more of an issue and much more widespread of an issue, as we've seen from the mapping we're doing. You will see areas that are becoming very regularly inundated, and that includes roadways and buildings as well. Roadways are some of already what's being affected, as in Pinellas County. Usually are the lowest spots, and they'll get, sunny day, no storm event, they'll get some high tide flooding during what they call the king tides, which are the highest high tides of the year, when I believe the moon is closer or in alignment with the sun in a particular way. So yes, it's very much an issue, and will continue to be more so as we go forward. Justin, I don't know if you have anything to add to that from facility
Just
level.
that, yeah, I mean, both tidal change and storm surge change are a problem, and we do look at them both, and we would just have varied approaches to how we're looking at and what the particular critical thresholds are with a piece of infrastructure. One of the examples we did not dig into for a roadway was looking at the storm drainage system for the roadway. In that case, storm surge is a problem. I mean, you'll get water in the storm drain system during storm surge, but it's not that critical of an issue as long as day-to-day it's functioning. But when we look at the tides, it becomes much more of a problem because every day this storm drain system is not properly functioning because of the tides. So I think the short answer is it depends. It depends on what we're looking at, but they both are a problem, and they are both a problem in Florida.
Thank you. We received a lot of, sorry.
Well, I was going to say, I believe there was a second part to that question, but I can't remember what it was, if you wouldn't mind reading it.
Does the surge analysis include all effects of tides, surge, and sea level rise?
Yes, it does.
Okay, fantastic. We have a lot of more questions. We're a bit over time. I will take the last questions. All the remaining questions will be answered directly by the presenters. The last question is, when looking at floodings, do you deal with the co-occurrence of high tidal water levels and storm surge water level occurrence in a simply additive approach?
So, okay, so that's a good question. That's starting to get into the statistics on how we compile what is a 100-year storm. So statistically, you are going to see the peak 100-year being a coincidental analysis with on an elevation-based standard with the high tide. So as we would take a deeper dive and look at currents, velocities, and other things, depending on what we're designing, we might look at different scenarios where we would be coinciding a surge with a low tide or a mid-rising tide or a high tide. But typically, if we're talking peak flood elevation for a particular return period, we are going to set that as being coincidental with high tide, as that being as appropriate.
Okay. Thank you for this. So we are at the end of our webinar session. Please feel free to follow up directly with Chris and Justin via the contact details shown on the screen. And I would like to thank all attendees for joining today. Thank you very much for your time. And thank you, Chris and Justin, for a fantastic presentation.
Thank you.